All right, I'll write that on board. That's solubility.
Well, let's start with assigning oxidation numbers. Because if you can assign oxidation numbers, then it makes identifying the oxidizing and reducing agents easier. So we're going to practice with assigning oxidation numbers. So there's a couple of rules when it comes to oxidation numbers that generally hold true. And let's start with the rules that surround oxygen. Do y'all know any, like, what is the typical oxidation number for oxygen? Yeah, so -2 or 2 minus, however you see it. So that's typically what oxygen is. But there's a couple of exceptions. There's two main ones, and they're very obvious to us. Okay, one of them is not so obvious to see. The first one is if you have oxygen bonded to fluorine. Like typically this one's going to have an oxygen with an oxidation state of +2. That's typically +2 because it's typically bonded to fluorine. So I kind of gave away the answer to part A already. So that's one exception. And the other exception, you all know what the other one is? Peroxide. So peroxide has O2 2 minus, and you might be saying, hey, it's still a -2, but actually it's a -1 because you have two oxygens. Peroxide can be broken down into two oxygens, each one having a -1 charge. So in this case, oxygen has a -1 charge. And you might see it as O2 2 minus because you're taking into account that there's two oxygens, both of them have a -1 charges. All right, hydrogen, there's some rules for hydrogen. Do y'all know what those rules are? Yeah, so for hydrogen to be a +1, what does it have to be bonded to? Non-metal, so any non-metal. So it could be carbon, absolutely anything. And it's pretty obvious to see when it's -1. It's when it's bonded to a metal. And it has to do with metals are more likely to give up their electrons than hydrogen is. So when hydrogen is bonded to a metal, something like sodium hydride, the sodium has a +1 charge, and the hydrogen or the hydride anion is a -1 oxidation number. So you're typically going to see that one in ionic species. So now we should be able to figure out oxidation numbers knowing those rules. So what's the oxidation number for each element in the first one? Okay. Oxygen +2. That's correct. It is one of our exceptions. And for fluorine? Yeah, -1, right? So fluorine with the -1. So we have two fluorine with a -1 charge. That's going to cancel out the oxygen with the +2 charge. So what about B? Yeah, so hydrogen's +1. So hydrogen +1. So fluorine's +7, but how do you know that?
Because the oxygen +2 is -8, and then the whole acid or that whole electron has a negative charge to it. The +7 or the -8, -1.
Yeah, so we have 4 oxygens. Each of them have a -2 charge. So we see that we have a total of -8 charges so far. Right? -8 from the oxygens. And then our one hydrogen adds 1. And then our chlorine, which we're going to solve for, is unknown, so it's X. And this equals the total charge of the compound, which is 0 in this case, right? Because it's neutral. So this equals 0. You solve for X, you get X equals +7. And that means chlorine has an oxidation number of +7. See how we did that? Okay. Let's go on to something a little bit more interesting. Let's go to N. So what is the oxidation number for platinum? +4. Okay, +4. How did you get that?
Because 6 fluorine -1 charge, and that charge. No, it's
So we have 6 of those. So that gives us a total charge of -6 plus our unknown equals the overall charge of -2. X equals +4. X being our oxidation number for platinum. So platinum has a +4 oxidation number in that case. And let's go all the way down to number or letter P. What is the oxidation number of each phosphorus atom? Why do you say 0?
Atom.
So it's not just that, but if it's in its natural state, it's going to have an oxidation number of 0. So phosphorus comes in, it's tetraatomic. It comes with 4 phosphorus atoms. So in this case, phosphorus is in its natural state, so it's going to have an oxidation number of 0. So that's the correct reasoning. What about Br2? And what is the natural state of matter for bromine? Like, it's one of the only 2 liquids. It's one of the 2 liquids on the pair. So oxidation number for something in its natural state, again, is going to be 0. Go down to I, and I think we'll call it a wrap on oxidation numbers. And you can do the rest on your own. So where do we start? So we only have 5 oxygen atoms multiplied by its charge. We have 3 phosphorus atoms multiplied by its charge. And we have 10 10 oxygen atoms multiplied by each charge. And this equals the overall charge of 0. So what is the charge of, which of those charges do we know? Oxygen, and what is it going to be?
-2.
Yeah, so -2. What else do we know? Yeah, hydrogen is going to be +1. So we don't know phosphorus, so we're just going to solve the algebra. Euro get 3x equals 2, x equals 5. So each phosphorus atom has a +5 oxidation. Yeah. Cool. Next thing we wanted to do is titrations. Want to do this one?
Yep. I got some in mind. All right. 42.5 milliliters of HI solution is completely neutralized by 56.9 milliliters of a 0.79 molar barium hydroxide. What is the concentration of the original HI solution? All right, this topic, I think y'all are going to see a question very similar to this on the exam, just because it kind of knocks out multiple birds with one stone. In other words, it has like, it incorporates multiple topics on there. So we won't like to get tested on. Like for example, this does include titrations like acid-base reactions, the solution stored geometry, it has some molarity in there. And it also does types of reactions because you're going to be required to like predict the products and sort of know your soluble groups. All right. First and foremost, what type of reaction is this? Acid base, or a neutralization reaction, as it is called. All right. What is the first step in any of these polymers? So yeah, so like right out of balanced chemical equation. So in this case, our reactants are HI and barium hydroxide. And what two products do I have? Water. Water, and what else? Barium iodide. What is the formula? Yeah. All right. What are my physical states for everything? Like HI, what is that? Aqueous or I mean you're right, but there's a specific term I want to use. It's a what type of acid? Strong acid. Yeah. Remember your strong acids are HCl, HBr, HI, HNO3, H2SO4, and HClO4 minus. Those are your 6 strong acids. So if you see one that's not those 6, so HI is a strong acid, meaning it dissociates completely. So we would say this is. What about barium hydroxide?
Also strong base.
It is a strong base. Because remember, strong bases are your group 1 plus hydroxide and your heavier group 2. By heavier, we mean calcium, strontium, and barium. So here, this is also strong base. So this is also.
Don't forget about ammonia and H4.
Yeah, ammonium as well. So anything that can make a hydroxide soluble is a strong base. Yeah.
So like strong bases are more soluble, but then we learned that like hydroxides, like that when it's like combined with something else, it's already insoluble. So it makes a strong base soluble when it's like that hydroxide in it.
So a strong base, right? I said that anything that can make a hydroxide soluble. Okay. So this is your group 1 elements ammonium, and your heavier group 2.
That's the only thing that's soluble.
That's the only thing that makes soluble. So anytime hydroxide is bonded to any of those, it's a strong base.
Okay.
All right. Y'all should all know this. What is the physical state of water? Yeah, it's liquid. Oh, should know that. You drink water on the daily. What about BaI2? Was that soluble or insoluble? It is aqueous. Because iodine is normally what? Soluble or insoluble? It is normally soluble. And is barium one of your exceptions? No. So continue to be soluble. All right. Next point. Is this equation balanced? How do I make it balanced? Okay, now the 2 in front of the HI. So our iodines are balanced, so that's good. We have 4 hydroxides on our reactant side, not hydroxides, 4 hydrogens on our reactant side, and only 2 on our product side. So what can we add, and where should we add it? 2 in front of the H2O. So let's see if this is balanced. 4 hydrogens, reactants and products, we're good. 2 iodines, we're good. 1 barium, we're good. And 2 oxygens, good. All right, this equation is now completely balanced. All right. So now we have, we need to get concentration, right? Or in other words, molarity. What's the formula for molarity again? Yeah, so moles over liters. The units are molar, but molarity, the actual formula is the amount of moles of the solute you have over the liters of solution. Or in other words, moles of liters. So capital M equals, we say N for moles, or I just do MOL over volume. So moles over volume. But wait, we don't have any moles in the problem. So is there a way we can get moles with the information we have? How do we get moles?
Multiply 0.79 polarity times the 5.69 million, which you can very slowly.
Yeah, so that's a 56.9, but I get what you're saying. So you multiply the molarity by the volume, right? Because if you rearrange this equation, you'll see that moles equals molarity times volume. How I got that was I multiplied both sides by the volume. All right, so as David said, we can convert the milliliters to liters. So 56.9 divided by 1,000, that's 0.0569. Then I multiply that by 0.75. And if I do that, you as well should get a mole amount of 0.044951 moles. And what compound is this mole number corresponding to?
Barium hydroxide.
Yeah, this is the moles of barium hydroxide. BaOH. Now we're trying to find the concentration of HI, right? So is there any way we can get from moles of barium hydroxide to moles of HI? Yeah, the multiple ratio, which is what in this case?
It would be the moles times 2 moles HI over 1 mole of barium hydroxide.
Yeah, so it's a 2-to-1 ratio. So for every 1 mole of barium hydroxide, there are 2 moles of HI. And if you're confused as to how I got these numbers, these correspond to the coefficients on the balanced chemical equation. So if I multiply the answer I got before by 2, I get 0.089902 moles of HI. All right. Now, what's our final step to get concentration?
By default.
Yeah, divided by the volume, which in this case is going to be 42.5 milliliters, but we have to convert it to liters. So 42.5 divided by 1,000, which if you do that, I'll just do it. 42.5 divided by 1,000, so that should be what, like 0.0425. Yeah, 0.0425 liters. So if we do that, we should get a final answer, and somebody can confirm with me if this is right. 2.11. Also, we're done, right? That's it. Or yeah, where this thing is called the neutralization reaction. So we say the acid neutralizes the base. But in terms of significant figures, are we done? No. So how many significant figures should my answer have? 2, right? Because of what number? 0.79. So this would be 2.1 molar HI. And that would be fine. Any questions about any of that?
So for titration formulas, do you not use the F1, V1, F2, V2 formula?
So ordinarily, the M1 V1 problem is used as a shortcut. So yeah, that would be used as a shortcut. The reason why we didn't use it for this problem is because M1 V1 assumes 1-to-1 molar ratios across the board.
Okay.
So in other words, all your coefficients should be 1.
Okay.
This is the way to do it if you don't have a 1-to-1 ratio. But if you do, then M1 V1 is a quick way to check yourself.
So acid base reactions never have a 1-to-1 ratio, did they?
I mean, not really. I can give you an example of one with the 1-to-1 ratio right now. HCl and NaOH, for example. This will give you H2O and NaCl. This would be a 1-to-1 ratio. You looked at it. So, yeah, general rule of thumb is this way will get you the right answer every single time. But if you write out your balanced chemical equation and see that you have 1-to-1 ratio, then you can go ahead and use that one. Anything else?
The 1.0419.
So what I did was I multiplied this 56.9 number, or I converted it to liters first, since molarity is moles over liters. So I took this number, converted it into liters, which was 0.0569 liters, and I multiplied it by the concentration here, the molarity. Because if you look at this rearranged form of the equation, the moles equals the molarity times the volume. Does that make sense? How I got that? Any other burning desires?
Like I said, you're gonna go for the last problem of the quiz we said the last time.
Quiz, yeah. Quiz is pretty much similar, or that problem is pretty much similar to what we did right now.
Oh, really?
Yeah. Well, yeah, I can.
Oh, it was on your iPhone.
Yeah. In 1 second, I'll get my iPad connected and then we can do that problem.
Feel feeling confident about your next test. Good talk. No.
Yeah, that did not sound very confident to me.
This is literally a foundation example.
Yeah.
It's the thing that, like, it's kind of, it's whatever. Like, I don't get the newer stuff, because then you're gonna get all of it, so like. Right now, we're just going over the same stuff, basic chemistry or high school. So now it's getting stuff that we didn't hear about. And it's part of the teaching process rather than I'm reviewing the same thing over and over. Which I mean, I don't mind, but I like getting into the more difficult stuff.
Yeah, this next unit after exam 1 is going to be very math heavy. So yeah, like even like heavier than it is now. All right. So as y'all can see, it is pretty much a very similar type of problem. So, here, all right. So it says, how many milliliters of 4 molar barium hydroxide would be required to neutralize 10 milliliters of 0.095 molar HBr? So this is sort of the same thing, right? Except instead of molarity, we're using instead of solving for molarity, we're solving for volume. It's the only main difference here. So what is our first step again? Balance the equation. So you have HBr and the barium hydroxide as a reactants. What are the products we will get? Water and what else? Yeah, what's the formula for that? VABR2. What are my states again? My states of matter. Yep, aqueous, liquid, aqueous. So remember HBr, also one of your 6 strong acids, so it's going to be aqueous. Barium hydroxide, same base from before. Well, already know it's a strong base. Water's a liquid, I mean, obviously. And then barium bromide is aqueous because it's bromine's normally soluble, and barium is not one of your exceptions. I don't know why my notification's coming up there. That's weird. All right. Anyway, we'll be required to neutralize 10 milliliters. All right. So again, we need moles, right? But we don't have moles given to us in the problem. So is there any way we can get moles from the information we have? And what is that way? Here's sound molarity. So moles equals liters times molarity. So again, we got to convert our milliliters to liters. So that's 10 divided by 1,000, which equals 0.01, times your molarity, which is 0.0950. If you solve that out, you get an answer of 0.00095 moles. And what element does this correspond to? Sorry, not element, compound. HBr. So this is the moles of HBr. But we don't want moles of HBr, or we don't want moles of anything, but we want the volume of barium hydroxide. But to do that, we need to get to the moles first. So is there any way that is humanly possible to get from moles of HBr to moles of barium hydroxide? Mole to mole ratio. But you will recall that I forgot to do a step. What is that? Balanced chemical equation. So how do I go about balancing this? Two on the HBr and two on the water. So let's see, four H's, good. Two bromines, good. One barium, good. Two oxygens, good. All right, our mole-to-mole ratio is now up to date. All right, so now that that is up to date, what is our mole ratio concerning HBr and barium hydroxide? Two to one, 1 to 2, same thing. So for every 2 moles of HBr, there's 1 mole of barium hydroxide. That's basically all the balanced chemical equation is telling you. It's a ratio. So if we divide that by 2, we will get 0.000475 moles of, in this case, barium hydroxide. All right. There's a final step we got to do. We got to get from, so we have moles here and molarity. So how do we get volume? Yeah, so molarity, right, equals moles per liters. So the liters, if we multiply both sides here, then we divide both sides by the molarity. We will get that the liters, or in other words, volume, equals the moles over the molarity. So if we solve that out, we will see that we have our moles 0.000475 over our molarity, which is 4.00. So we divide this by 4, we'll get our volume to be 0.00011875. But what are the units here? Is it milliliters? Liters. So we're done, right? We're done with the problem? No, because it's asking for milliliters and not liters. So what do we do to get from liters to milliliters? Times 1,000. So if we were to do that here, for every 1 liter, there's 1,000 milliliters. Or a quick way to do it, you just move the decimal point to the right 3 times. So times 1,000, we will get 0.11875 milliliters. Which is a very small amount of milliliters. I don't know. Right. Any questions about that? What about signals? You tell me. All right. Raise y'all's hand if you think it should be 2 sigfigs. Raise your hand if it should be 3. 3s have 1. And that is actually correct. There should be 3 significant figures. Because there's 3 right here in the 4.00, because you count both the zeros because they're after the decimal point. 10.0 as well has 3 significant figures, and so does 0.095. So it should be 3 significant figures overall. So if we do our sig fig stuff, I'm gonna put the final answer over here. Should be 0.119. All right. Any questions, comments, or concerns? Right. That is very cool. All right, what other topics do we have remaining on the old chopping block?
How do y'all feel about the stuff that we've done so far? Do you feel more confident? If you said something that's up there, do you feel more confident or not at all?
Yeah, that's fine.
Alright. So how about I'll scroll through this slowly. And if there's a question you want to go over, I'll just say it, okay? Number 1. I did that one. iPad is very light.
Can you scroll back up to number 4? That is a type of reaction. So that reaction is best classified as what? Double displacement, yes, but more specifically, what is it?
What's the form?
That's a precipitate. So it's what type of reaction? Precipitation reaction. Yeah.
Go add another check mark. So it's good that you said that, because if this was on the test and it's multiple choice question, and one of them says double displacement and the other one says precipitation reaction, you have to choose between, and there's not like an answer choice that says both A and B, then you have to choose between the two. The more right answer is going to be precipitation reaction, because double displacement reactions can occur where there's no precipitate that's formed. So because this one has a precipitate that's been formed, it's important that you indicate that in the type of reaction.
I mean, I just saw a case where the former was true, the acid-base reactions, because there was no precipitate there, but still there's no reaction.
Yeah. How y'all feel about 6? Yeah. So, what makes a strong electrolyte? What are the classes, subclasses of a strong electrolyte? Strong acid. All right, let's start with strong acids. So, strong acids abbreviated SA is, what are the 6 strong acids that Rich mentioned earlier? Yeah.
H2SO4.
Yeah, hydrochloric acid. And one more.
HBr.
Oh, yeah.
It's like HCl, but not really. There's more atoms on the CL. How many somethings are there though?
And
It's one of those 3.
once you tell us 6 strong acid, everything.
All right. Say it louder.
Yeah, what's the name of that though?
hydrofluoric acid, or no, just fluoric acid.
So fluoric acid. So those are strong acids. Strong bases include what?
Group 1, under group 2, ammonium, and hydroxide.
That's a better lesson.
When they're attached to hydroxide. Okay, so group 1 elements attached to hydroxides, calcium, strontium, barium attached to hydroxide, and ammonium attached to hydroxides. And then last one, there's one more class. So this just comes down to solubility. If your solubility rules tells you it's going to dissolve in water, then therefore it's a soluble salt, meaning it's a strong electrolyte. So this one is all solubility rules. I can't really, well, I could, but I'm not going to waste our time listing out every single soluble salt. Just know the solubility rules. So that's strong electrolyte. What comes after that? Weak electrolytes. And so you have weak acids one and weak bases together. So how do we know if an acid is a weak acid? Yeah, it's not one of the 6 strong acids, so that's pretty easy. Okay, so we look here. It's not one of those 6, it's going to be weak. Now, what about a weak base? Ammonia, yeah, we're talking about nitrogen based compounds. So ammonia, maybe something like this, methylene. Basically, in this class, you're going to see nitrogen based compounds or organic compounds like methylene as the weak bases. Okay? And then we have non-electrolytes. And this includes what? So things like glucose. Glucose will dissolve in water, but it's not going to be dissociated, so it's not going to produce electrolytes. If that makes sense. What else? Give me one more of the covalent bonds.
Acetone.
Yeah, acetone's a good one. So, what type of pure about bonds? Those are the chemicals.
C3H6O. Yeah.
Like this. Just a shortened version of I'm not going to do it. And then there's one more thing of non-electrolytes, one more subclass. So we talked about soluble salts earlier. What do you think would be something, a type of salt that would not be soluble? Insoluble salts. So there we go. So again, this all comes down to solubility rules. If your solubility rules tell you this is not going to dissolve when putting in water, then guess what kind of electrolyte it is? Non-electrolyte. If they tell you that this is going to dissolve if I throw it into water, what kind of electrolyte is it? Strong electrolyte. So with that knowledge now, shall we go on to answering A through F? Yes, Michelle. Okay. We are so excited today. All right, first one, A. Calcium chloride. So, wait, did I hear strong base? Strong electrolyte, and what subclasses would fall under? You say strong base, why do you say strong base?
Okay.
Calcium with metal. It's not gonna participate, it's not gonna act as a base when you throw it into the reactor, but something like calcium hydroxide will be base, but not because of the calcium, because of the hydroxide. Yeah, so key indicators of a base are gonna be OH, so like we look at E, you see a hydroxide, but don't get that confused with C, ethanol, which is a covalent compound. All right, so this is a strong electrolyte. Right? B, about B. Strong electrolyte and one class of
Acid, strong acid.
strong acid, so it's a strong, interesting. Strong electrolyte. Because it's a strong acid. One of those. All right. Yeah.
So what's the possible A? It's like chocolate later.
Yeah. So A would be a soluble salt. So SS. Okay. If you're here, you know what SS means. If you're watching the video, you might know what SS means. But if you're just getting a PDF scan of this, you might not know what SS means. SS in this case, soluble salt. You know, stay a little bit of time. What about ethanol? Weak electrolyte includes weak acids and weak bases. Is this either of those? What do you want to say? If you were like, or I'm going to use that analogy, but if someone was forcing you to say something right now, that we're recording right now, what do you say? It's a weak acid or a weak base with involved. Different acid. If you said it was a weak electrolyte. It's not a base because bases include ionic compounds that have hydroxide as their anion, but this is a covalent compound, so it's not going to be the OH might trick you. You might think, oh, it's hydroxide, but it's in a covalent compound, so it's not in a hydroxide. It's actually an alcohol. So with that, what do you think it is? Weak electrolyte, non-electrolyte. There we go. Right, because will this dissolve if you put it in water? It will, right? So, but that doesn't tell us if it's an electrolyte. What tells us that it's an electrolyte or a non-electrolyte is how much it dissociates in water. So when you think of dissociating, you think of when you make spaghetti, you put table salt in the water. Maybe some of y'all don't do that, maybe some of y'all do. Sodium chloride start like this, but then they break off, they dissociate. When you put ethanol in water, it's just going to stay ethanol. It's all one thing. Not even like two pieces. It's going to dissolve, but it's not going to dissociate. Right? What about this one over here? And I gave you a name of this. It's called formic acid.
It's gonna be weak, so it's not one of the structures.
Exactly. So we know it's an acid. The fact that they told us, or I told y'all, and typically on a test they'll kind of give you this parentheses. They don't expect you to know what HCHO2 is, right? So they will tell you formic acid, and because you see formic acid, you think, all right, is this a strong acid? It's not one of the 6 strong acids, therefore it's automatically a weak acid. It makes it a weak electrolyte. So All right. Class 2. Strong, and why do you say, okay, what class? Strong base, because it's a hydroxide compared up to a group 1 metal, okay? So strong. So whenever you see OH, make sure it's an ionic compound before you call it a strong base. But maybe one day you see something like do we see a metal in this problem? It's metal. Is it going to be a strong base? No, right? Because hydroxide, when paired up to titanium, is insoluble. Well, hydroxides are generally soluble. Titanium is not a cation that makes it soluble. So hydroxide is going to be insoluble, like in general. Last one. Insoluble. We got one vote for insoluble. I don't know how I feel about that answer, but I'll let everyone else do it. What do you think, David?
Because lead 2 plus.
There we go. You're right. You're right. I wanted to get some other people's brains turning. So chlorides are generally insoluble or soluble, right? So we know chlorides are generally soluble. There's exceptions that will make chloride, bromide, and iodide insoluble. And it just so happens that when you pair it up to something like lead with a +2 charge, +2 specific, if it's +4 lead, it's not going to be insoluble. But if it's +2 lead, it's going to make it insoluble. So this is lead paired up, or this is lead 2 paired up with chloride. So this is going to be insoluble, which classifies as what kind of electrolyte? I hope y'all got a little bit more comfortable with non-electrolytes or just the class of the electrolytes from today's session and from Monday's session. You're definitely going to see some problems on it because this might be one of the newer things you've learned. Maybe you didn't go over this in basic. So we're going to test you on the things that you just learned, the things that you knew semester. All right, so make sure you're comfortable with all those. And you see how it tied into solubility rules, and that can tie into creations or types of reactions or net ionic equations. So if you don't know your solubility rules, you might be missing out on a lot of points on this exam because there's so many things that they can ask you. Solubility rules is needed to know how to answer this question. So y'all are going to study this, right? You got a little over a week to get it down. Are there any questions? Yeah.
So like non-electrolytes, ethanol, they don't associate, like they're still soluble, right?
They dissolve in water.
Okay.
But they're not going to dissociate into electrolytes.
Okay, because it's no metals, there's something ions in there.
Yeah, it's not an ionics. Okay. Acids, even though there's no metals like HCl, it's still such a strong acid that when you put in water, you can associate the H3O or H plus and HCl. So just be cognizant of that.
You're confused as to like why they actually dissolve. We don't go through that in this class, but like they can.
If you be interested in like very much like ethanol.
Yeah, you probably won't see anything like that. Ethanol. There's not much that we do that for the type of reaction. It doesn't do double displays when you single displays. You can do like a combustion reaction, but usually it's going to be in gas is one. But they'll usually let you know what it is. Yeah.